So, greetings of the day. Now, today we are going to see what are all some of the challenges and opportunities in the 5G. Okay. So, first challenge when comes, front end RF front end point of view. Okay. So, so I'm going to discuss more of front end challenges and opportunities. So first challenge will come in antenna design, because that is where the conducted energy is being radiated, it is a therefore the effective wireless communication can happen. Okay, so first and foremost example, important thing is that antennas. So because we have a lot of frequencies, lot of different kind of subcarriers, different multi-band operation, different bands like a millimeter wave, sub-millimeter wave. In sub-millimeter wave, there are multiple bands, and also in millimeter waves there are multiple bands. So in that so it will have a huge requirement, and also bandwidth also at the same time, bandwidth, dual polarization. So many things are there. Okay, so now let's have a look at the so how antennas are evolved from 2G to 5G. In 1G, I'm sorry, it's 1G to 5G. So in 1G, you can see that, see, there were external antennas, okay, helix antennas and loop antennas kind of thing. Okay, so external antennas, so therefore the coverage was too good, because when you have earlier and all, we used to have towers at 40 kilometers, but still the coverage was very good. So if you can go on the top of the building, then you can get some coverage. Okay, so in India I would say BPL time. Okay, BPL had a network, initial first GSM network. That time many people used to have it's kind of 1.5G or 1G, like something like that. Okay, many people have these kind of phones. Okay, so external antennas. Okay, that time the printing technology was not implemented. So in 2G, what they did is they brought the external antenna inside. See, in 2G also we had some of the external antennas, phone like in Nokia especially. So that was it's a much compact antenna compared to this. It's a kind of monopole antenna, but here they used helix, and then the compact antenna they made. But then they on the go, there are multiple research was going on that time. Then what they did is they brought in these antenna inside. Okay, in the phone itself. Okay, next is the 3G. So 3G, what happens is, so 2G itself we have multiple bands like 1800 and 900 bands. Okay, so in that itself, so it has to cover that much range, and with a certain gain and other matching parameters. So so bringing in this antenna to the inside itself, at that time it might be a huge problem, because you will have a space constraint. That time all the components were very big, and then and also frequency band itself high, like then so in order to bringing in with the multiple antenna, it is quite that challenge that point of time, because and now its technology is much evolved, and in 3G what happens is it has to not only cover 3G but also the 2G, as 2.5G, like 800, 900 and 900 and so 1800, 2100, 2500. So several multiple bands were there at that time. So, and also along with these things, GPS antenna has to be there, Wi-Fi, Bluetooth, and so on, near field communication. That time itself we had some of the phones had some limited near field communications. That time we used to send like I think Samsung phones or Nokia phones, they had interfaces. That time we used to send the files through that. Okay, anyway it will connect through Bluetooth, but there are some more interfaces are there. So these technologies has to be antenna has to be installed with these many technologies. Okay, so that time it was complex. For example, iPhone 3, okay, now when that time launched, all the antennas were there in the cover, like an outer, side cover. Okay, so that time what happens is, whenever we touch the antenna, when touch the phone, when hold the phone and then talk, that time there were a lot of interferences. That's why they, they even had given free of like there was multiple problem, EM problems had happened, because when you touch that those antenna part, that time you are acting as a ground. So that time your signal gets disturbed, and then there were multiple noises were generating. That time what they did is they had given a special cover, so that it is kind of might be, it should be as a shield. So like a kind of shield kind of thing, so that it will not disturb the signal. But here, so it also gives this hold. Okay, so that cover they give for free of cost. So that much complexity is that antenna. So, and 4G, what happens is, so even more higher complexity, along with this whatever I told for 3G, along with that we have to go for 4G in multiple bands, 700 and 3500 and 3 gigahertz and 20.5 gigahertz, 2.1 gigahertz. So multiple frequencies they have implemented this 4G. So, and also here 4G, the MIMO come into picture, and so especially MIMO come into picture, and MIMO means what? So you will have multiple antennas, and so correlation between them. So many things are there. So you have to bring in. It has to work independently, and then you have to have a good isolation. So many things are there, and multiple bands also. So that was the challenge we faced in 5G, 4G antennas. In 5G, even much more complexities, because along with this 4G, 3G, 2.5G, if you are using as a non-standalone network, so then you have to support all these three. Okay, so and I don't think it will support 2G, 3G. It will support only 4G. Okay, so because it is non-standalone network, only 4G is supported. So in that case, what happens is, along with the 4G antennas, we have to develop a 5G. You can see that 5G, multiple bands are available, multi-bands and multiple frequencies, and dual polarization, and with a good cross polarization thing, and also beam forming. So massive MIMO array. So these kind of stuffs will come into picture here. They will discuss later. Okay, and this is where a mobile point of view. This is our base station antennas point of view. You can see that in 2G time we used to have earlier they used to have dipoles like this. So I think you can see dipole. I can just you can see here all were dipoles. Okay, so dipoles they were using, so because very low frequency like 800 900 megahertz. So it's not a very low frequency when compared to 4G and 5G, 3.5 gigahertz and other things. It is very low frequency. That's why they used dipoles, and then this is actually used for 900 and 800 megahertz. So one array of dipoles will be used for 800, one array of dipoles will be used for 900. Okay, and also so you can see here that these are all the panel antennas will be used. You might have seen in the buildings, like in building solutions like shopping malls, theaters and other stuff. Okay, now when 3G came into picture, that time what happens is, so they have to support even existing technologies like 2G, okay, and also 3G. In 3G, whatever I said, here the Wi-Fi, Bluetooth and all will not come into picture, but you have to cover multiple band of frequencies. So along with that, you have to cover 3G to 4G. What happens is, so it has to cover entire thing. So with diversity, main, and so many things are there. So then they made 3G and 4G there were tilting unit, electrical tilt unit, because electrical you can tilt the antenna like a beam from remotely. So that also is there. So was supported. So you have to have electrical tilt unit support for 3 bands and 3 antennas. So like 4G and 5G. So sorry, 4G, 3G. So that's kind of stuff. So see how many ports are there, because one set of ports will be for 900 megahertz, one set of ports for 1800 megahertz 2G, and one set of ports will be for 3G. 3G itself multiple bands are available, and 4G itself, and then 4G one set of ports will be available. We have to support even MIMO also. So that's why this many number of ports are available. In 5G it is totally, so it's complex, because you have to support multiple ports. Here also we standalone and unstandalone will come into picture. Multiple number of ports, because you are working with arrays, massive MIMO arrays. So, and it has to support beamforming. So beamforming networks, you can see here that, so this is radio and this is the antenna, and you can see the complexity, how big is this. Okay, and in India they made a 32, Samir has made, I got this picture from online. So 32TX, 32RX, see how many cables are coming out. But it's so compact structures, because it's a millimeter wave thing. I think it should have been done in millimeter waves, because if you are doing in sub 6 gigahertz, it will not be this much compact, it will be even more bigger. Okay, and you can see here that, so printed antennas are available. And so apart from this, so you can see that, say, these many antennas are available, phone BCB, multiple stuffs are available. When you see, you can see here LT MIMO horizontal polarization, LT MIMO vertical polarization, LT. So this kind of antennas, CP, C5, CDMA antennas. So because it has to support CDMA also, some operator will want that. So GPS antenna, Wi-Fi TX-RX antenna. So how many antennas are there? You can see that along with the phone PCB. So along with the phone PCB, it has to be integrated. So how complex is this? And you can see this graph will show you. I think I took it from Fractus Antennas website. So this graph will show you how we evolved. See, this much big antenna has become kind of small structures. Okay, so these are all the 2.5G antennas and then 3G antennas. So then how it became so. And so this I think we have discussed earlier also, because this is the RF chain of this baseband processing, DAC and RF, and then RF array and beamforming structures. Okay, I think yes, we have discussed enough in the previous lectures. Now, so RF and antenna systems, you can see that active integration of, so first point is that active integration of miniaturized RFFE or a front end. So active integration and miniaturized RFFE modules. So that is where we get with lot of challenges, because we have to bring in matching between all those components like amplifiers, mixers, low noise amplifier, receiver chain, low noise amplifiers, IO filters, local mixers, local oscillators. So multiple components will be there. So you have to bring in matching, because antenna works with for example so different impedance. So output of the amplifier will be different impedance, so it has to get matched with all those components. So that's why it's where so system on chip, system on product kind of array also coming in, because we cannot print separately design array and then integrate with this boards, because it will be very tedious job. That's why system on chip and system on product concepts are coming up, because one layer will be one board set of components along with that array elements, and the other layer will be on set of components and array. So likewise, so multiple layers will be there. So each layer, so these antennas are mounted. Next is the beamforming and beam switching. So beamforming has to be done with the proper algorithms, and then also it should be supported by the antennas. So here, see, you can see that in 5G, beam acquisition and tracking and beam refinement, beam feedback, beam switching. So all these are related to like algorithms and methods to devise this. Okay, and also here radar concepts also will come into picture. It's not a new, it's a radar concept. So because in radar we used to say that angle of arrival, angle of detection, angle of arrival, and then we have to detect, say, because if you want to detect the enemy radar, so that time we will send the signal and get the response from them, and then we have to refine our antenna position and beam position, and then we have to follow that enemy radar or enemy fighter jets or anything. So we have to refine ourselves, and then we have to refine the beam then and there. It will be much faster than what we are assuming, because so those concepts are implemented in even in 5G also. Yeah, just no. Okay, as we saw that, okay, front end has very active integration, miniaturized front-end modules. Okay, so one more point I want to make sure that, say, next is that yes, was system on chip and system of package, system on pack, like PCB or package. Okay, for an array. So why we go for that? So generally, how array being designed? So first of all, what we will do, so what sort of gain is required and what sort of beam is we are looking for, and those, and what is based on that, size of the array will be dictated, and how many number of elements we are going to use, and all those stuff will be coming. Okay, so array means it's not only just a PCB printed over there, or some of the dipoles or there, so not like that. Okay, it is basically array has beamforming networks, phase shifters, power amplifiers, and many more are there. Okay, interconnections, several things are there. Okay, so so we have to consider those things, because in system on chip and system on package, in general, what I understood from the literature is that how they are employing, along with the front end modules. So how they are integrating the how they are integrating RFFE front end models with the baseband systems, or receiver chain or transmitter chain. How they are doing is that, so system on chip concept, like one layer you will be having antennas, another layer will be having some of the front baseband module, baseband processing unit, and other layer we may have some other components. Okay, for transmitter chain or receiver chain, so anything. Okay, and for beamforming networks also you may have. So through vias, so all are interconnected. Okay, so that's where this system on chip and the system package, or PCB is coming for coming up in this area. So what is the opportunity for the young researcher or RF engineers is that, so you can explore this kind of multi-layer design, and integrating several components, having a wide range of components like amplifiers, power amplifiers or low noise amplifiers, beamforming networks, array antennas, everything. So integrating those. So in those area, we have plenty of opportunities, because coming up for the in respect of 5G, because so it is very, very highly complex, because so when you design alone, it is a different case. So when you are integrating, then each will talk each other, and each module will behave in a different way, because when you are testing in the isolated mode, it will be a different behavior. But when you are integrating with the other modules, then it will behave differently. So we have to bringing in proper matching. So several aspects are coming into picture. So this is the challenge where so a lot of research open problems are coming up. So and even industry looking for a person who can handle these issues, and I think you can see in LinkedIn or anywhere. So most of the JD will have these kind of requirements. Okay, and next is beamforming, beam switching. Okay, so beam acquisition. So these are all kind of initial like when UE getting into the 5G node B coverage area. So these things will happen. So how this will happen? Beam acquisition tracking. So there are a number of parameters are available. One is as far as I know. So okay, so there may be multiple things might be available. You can refer in other websites or papers. So so first what it will do is, when the mobile switch on, there are attached procedure will have several procedure will happen, protocols. So several things will happen, because so base station will send some of the control signals, and UE will try to send the information to the node B. Node B will respond to that, and many things will happen. So in 5G especially, what will happen is, apart from that, so because earlier we had a cell coverage. Okay, when you enter to the cell coverage, then you don't have to worry, because you have for example, for example, in 4G or below 4G or 3G, this is the tower. There you have 3 antennas. There you have 3 antennas. Okay, and you can see that this is the 3 antennas. Okay, So when you enter this particular cell, it will have a coverage of how about minus 62 plus 60 or minus 92 plus 90. Okay, so when you enter, when you device, a mobile or a user will enter to this cell site, then no need to worry about coverage and all. You will have an entire plenty of coverage. But that is not the scenario in 5G, because here we are talking in respect of beam forming concepts. So what I do, because I will not have a unless I request for coverage. So I will not have that. So that's what this process will happen. So beam acquisition, tracking, and beam refinement. How does it happen? See, there are a number of parameters that I think you might have studied in networks. Like one is channel state information, reference signal. So channel state means how the channel is. I think we will see a channel state information, reference signal, and then see where the UE is, and based on the RSRP values, so a number of values are the channel state information, reference signal, channel state quality, RSRP values, and RSRQ values. And based on that, so it will node B will try to detect the user. Okay, so first what thing will happen is beam acquisition tracking. So which means what? So when UE enter into the 5G site, so for example this is the UE. Okay, so for example initial position was this UE. Okay, forget about this. So where for my beam is actually 1 second, because it is confusing. Okay, so now let me explain. So for example, so when UE at this place, okay, so initially what happens is, so it will try to acquire closest beam, okay, whichever beam is available nearby, or which means whichever beam having very good strength. So obviously this is having more strength for in respect of this UE than this beam. Okay, so that is called as beam acquisition. Okay, then what it does is, so then when for example when you UE in mobility, what happens is, so it will track. Okay, and beam refinement, how does it happen? For example, when my UE position is this, so it will try the beam will, what will happen is, we will try to refine beam towards this direction. Okay, so then it will come like this. Okay, so till it get the beam refinement. After that what happens is beam feedback. So it will try to get, this will go to and fro, because it will try to get beam feedback, then it will refine the beam again, feedback, refine the beam. So these are all happens is SSB blocks and channel state information, reference signals. So these signals, these signaling things will take care of these things. Finally, beam switching. So switching means what? When UE in a movement, okay, so it has to track that also. Okay, the beam has to go along with the UE till the UE leaves your cell site. Okay, and capture the cell edge. So why we are doing this? Because in 5G there is a promise that cell edge data rate is very high, but in 4G it is not like that. Because for example, you have a device, and when you move towards the cell edge, so you will not get very poor coverage. Because why? Because see, the coverage area is very large, so therefore the power at the cell edge, okay, for receive power at the cell edge, it will be very minimal. But here the beam, when you are at nearby or and so there will not be much variation in the power, because you are pointing the beam towards the UE. Okay, so that will have a very high gain. Okay, and so that's why so cell edge data rate could be ensured. Okay, next is that CAD modeling and analysis. CAD modeling means what? So computer aided design. So you might have studied in mechanical perspective. CAD model is is for mechanical aspect as well as the electrical aspect as well, EM aspect. Okay, so when you design CAD modeling, what I mean here is, so like when you design PCB, so and analysis, so as I have been telling before, say SOC, SOP and all. So when you design the PCB modules, like along with the antenna arrays and the massive MIMO and several amplifiers, oscillators, so mixers, IF filters, so RF chain and baseband processor, so several things are there. Okay, so that time, so we cannot just directly design in the paper and then just fabricate. No, so we cannot do that like that. So we have to go for CAD modeling. So we have to model and see how and analyze that scenario before we fabricate. Okay, so that is done through CAD modeling and analysis. So why it is challenge as well as the it will give a lot of opportunity, because it's highly complex design. I think we have discussed enough on that. So multi-layer design, large number of vias, because you will have plenty number of vias. So vias also, you cannot just put just like that, because every via will have impact on every component, every other component. So that we need to take care during the CAD modeling and analysis. So because we have to do plenty of analysis, so that's why if you have very good experience in these things, multi-layer design, vias, generating vias and interconnecting layer by layer, you will get plenty of opportunities, because so that is where real design is involved. Real design engineer's role is appreciable, because so if you design properly, improperly, then what happens is, so the entire PCB will get lost. Okay, that's why. So next is that thin substrate is required, because as we are going for multi-layer design, so we cannot have a thick substrates and all, because then it will become bulky. Then design will not be feasible. So when you have a thin substrate, the problem is you will not have a higher bandwidth. So that also is there, because thin substrate means lower bandwidth, thick substrate means higher bandwidth. So in principle, okay, so that we need to take care, because we that element will take care, and our modules will we have to be taking care. Okay, so that we have to ensure in during CAD model analysis, that so when you use thin substrate, then we can go for several layers, and it should not affect the bandwidth as well. So see, and number of vias also, when you change the number of vias, then there are definitely the effect will be there. Okay, next is computation complexity and time, because computation complexity, it will be much higher, as I have been discussed now. So you can see that multi-layer design, how it will be complex, because and solver will take much time to do that. So so lot of simplest methods are evolved, because in order to analyze these kind of complex structures. So there is an opportunity for engineer, like computation, electromagnetics, or electrodynamics engineers. So because to solve these problems, like multi-layer and large which is having large vias and thin substrates. So in order to analyze that layer by layer, and finally we have to combine the effect of each layer and the whole system. So it will take much time. Okay, next is that antenna perspective. So how antenna, because in 5G especially, we are having we are going to deploy a massive MIMO array. Okay, so massive MIMO array, it does not come, what we have to do before we design an antenna. So what we have to do first, okay, we have to sense the requirements, like so what are all the, how much gain you require. Okay, and what beam, what is the beam width, which means gain. If you are known the gain, then beam width will be automatically dictated. And so and requirement of, for example, you have a oh sorry, you have you have a cell site here. So what should be the gain over in this point, what should be the gain in this point, at the cell edge. Okay, that also we dictated. And what sort of beam width we are going to handle, because when you have a high gain, then narrow beam width, low gain, moderate gain, somewhat broader bandwidth, beam width. And when you are having a small gain, it will be a broad beam width. So all are interlinked parameters. So that we need to consider. So what sort of gain you are going to employ, what sort of beam width you are going to handle, and so what is the polarization you are looking for. For example, in general, I think in 5G it is in principle it's a dual polarized, because as I mentioned in the previous presentations, that you need to cover vertically as well as the horizontally, azimuth and as well as the elevation. So then therefore the dual polarized is must. And apart from that, so what you have to do, you need to decide which algorithm you are going to deploy, because so algorithm development is the one which is crucial, because here as I mentioned in the previous slide, what I'm doing, beam refinement and beam switching is happening in a fraction of seconds. Not even seconds, fraction of milliseconds or nanoseconds, because when a vehicle moves 500 km/h, so because now they are promising that 500 km/h can be supported. So that kind of speed, more than 500 km speed. So for example, bullet trains. So that time, beam switching, it should be, nanoseconds, okay, or picoseconds. The switching speed should be picoseconds. So the algorithm should be that much efficient, and so this is where, if you are good in signal processing engineer, so then algorithm, if you are having a very good interest in developing algorithm, then you have plenty of opportunities these areas, because switching speed and what sort of beams, different switching speed. Along with that, you have different kind of beams, because you are not targeting only one customer. So at the same time, you will be targeting another customer who is stable also. One customer is roaming in bullet train, another customer is stable sitting here, another customer is slowly moving in the car, another customer is you have plenty of scenarios. So therefore the beam requirement also keeps on changing, because as a user getting into the particular cell site, so like not cell site, like 5G node B, under coverage of particular node B. So these are all the requirements we have to sense before we go for any. And what is the class polarization requirement? What is the side lobe level you are looking for? And what should be the so antenna size should be, and because here you are not going to design only antenna alone, because you are going to integrate that with the radio itself. So what sort of requirements you will be having, because the size is limited and everything is limited, okay. And what sort of beam forming algorithms you are going to deploy, whether you are going to fixed beam or and phase shift, what kind of phase shifters you are going to use, as we mentioned in the previous presentations, like analog phase shifters, digital phase shifters. So multiple things are there. So first we have to see all these possibilities, like before we go for that. So before we go for high level design, we have to be taking care of these things. Next, what we will do, once having said that, so for next what we will do, we'll go for antenna element design. Okay, so once so everything is decided that okay, this many size of array I am going to deploy and this many elements, and so based on that, and then I should go for element design. So the element design play a crucial role here, because element only dictates the beam width and many parameters, like side lobe levels and bandwidth, gain, beam width, beam switching. So all the things are happening. Element design is crucial one. So you have to have element design. And feeding methods. So feeding methods, what sort of feeding methods you are going to use? Here definitely it's not just a corporate feed network. So it will be a multi-layer network. So several kind of complex feeding network methods you are going to use. Next is that impedance matching. Impedance matching is, achieving impedance matching is very difficult in 5G especially, because here its antenna is not alone, because when you want to match with the 50 ohm, that's okay. So because we always for paper we used to design for 50 ohm, okay, but it is not the case in the 5G, because they are going for you design for 50 ohm, then amplifier will be in output of the amplifier will be different ohm, then you have to go for a matching networks. So multiple things, it will be iterative process. So because bringing in impedance matching itself between your amplifier and the antenna is very tough task, because it will be maybe a 1 month effort or 6 months efforts for an expert engineer in this field. So So bringing in once you design the antenna separately, then bringing impedance matching is very very difficult. That's why people are proposing with the integrated antennas, like along with the amplifiers and everything. So whole chain they will design antenna also, because so that you need not work on impedance matching separately. Next is the element spacing. So that dictates the mutual coupling and what sort of side lobe levels, what sort of beam width, and what sort of gain. So that's what plays a major role. So and next is polarization. Polarization is, yeah, that's what I have mentioned. So when you deal with the dual polarized antenna, so you will have a cross polarization issue, and a dual polarized means, which means so you need to have almost similar kind of patterns in both the polarization. Otherwise, we cannot call it as a polarization, dual polarization, because and both the vertical, for example, vertical and horizontal. So you should have a same gain, same kind of sort of beam width. Different, like maybe scenario to scenario it will change. So that achieving that with the, for example, some scenario will come like this. Like in azimuth sweep you will have a beam width, a very narrow beam width. Elevation sweep you need a higher broad beam width. That scenario also may come up. So that, because for example, when you are covering building, there will not be much movement. Okay, so the elevation may not be the much movement will be there in the will be there with the user. So that time your beam requirement will be different. When you are under azimuth thing, so the beam requirement is different, because in azimuth means they are going on road. On road they can travel at any speed. But elevation means, so when you are traveling in building, so it will not be much thing. Next is the bandwidth. So again and again I'm stressing that. So when you design an element, so bandwidth, achieving water bandwidth with all those constraints is very difficult. Okay, and gain bandwidth, active elements. So active elements, because obviously we cannot go with the passive elements, like earlier we used to design an array with the corporate feed network, so they will have a very good nice pattern. So but now it's not the it's a different game. Like we have to employ several kind of active elements, because like phase shifters, Farad phase shifters, or MMIC based phase shifters, and and conventional phase shifters, like passive elements, like planar phase capacitor or inductor kind of combination. So several things are coming into picture. Next, diodes, and also varactor diodes, or many Zener diodes for phase shifting changing the excitation of the element design. Okay, because feeding methods, what it will take, feed network, what it take care of. So we have to excite the element with the particular amplitude and phase, so that you can achieve these beam width. Okay, this I think I explained in the previous lectures. Okay, next is the beam forming. So as mentioned in the previous slide, the beam forming is very 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 important, because as I mentioned, so if you are good in algorithm development, or if you are good in signal processing, then you can take up, you will have plenty of opportunities. Once so the industry, those who are working in 5G, they will easily absorb you, because algorithm development is crucial thing in 5G, because if you reduce the processing by 1 nanosecond, that is a very very big achievement, or will be very much appreciable by the manufacturer. And beam forming networks, as I mentioned in the previous slide, beam forming networks, whether you are going to use Butler matrix, which is a fixed beam switching, no, that is not that will not be a real-time case, because for example, how many beams you will fixed beams you will sweep, because when you are having a moving thing, so that time you cannot use just simply go for a Butler matrix. We have to go for a different kind of feeding networks. So next is that crosstalk. Okay, crosstalk, when it comes, so when two beams are collide with each other, for example, when two users are close, coming in closely, that time what happens is two different beams also will come closely, then it have to decide. So then sometime what happens is these two beams will talk with each other. So that time the crosstalk will come into picture. Next is antenna mutual coupling. So antenna mutual coupling, as I mentioned, so when your element spacing will dictate these things. Okay, element spacing, substrate characteristics, and what sort of So substrate characteristics means dielectric constant, loss tangent, and the quality of the material. So because anyway, obviously they will use some quality of very good, very high quality material. But still, so now we are working in different bands. So different bands, we don't know how much stable it is. This, for example, substrate may be very good in, for example, 28, up to 30 gigahertz. So if you use beyond that, so substrate will become because you cannot achieve a very good reliability, very 100 ideal case for very high bandwidth, very high frequency range. So that also matters. Okay, so mutual coupling depends heavily depending on the element design and element spacing, substrate properties indirectly, and the active components that we use for phase excitation and beamforming algorithms. So these are all and so when it integrated with the other amplifier components and other things, then mutual coupling is a serious problem, because that is where several studies are being it's a very good opportunity, mutual coupling analysis of antenna in array, massive MIMO array. So whether you are considering as a MIMO or MIMO means MIMO also we have a mutual coupling problem. So isolation should be very good enough between the MIMO, because massive MIMO array, what we talk, so each element is an array, phased array. Okay, so the one MIMO element between one MIMO and another MIMO element, there should not be a mutual coupling. So that is a serious problem. Next is impedance mismatch. Impedance mismatch is a very serious issue, because once you design antenna perfectly, then you can design amplifier perfectly, but bringing in impedance matching is very difficult, because for the required above set requirement, with the above set requirement like a polarization, bandwidth, gain, all those stuff. Okay, impedance matching. So bringing in impedance matching is very difficult, because one will work, another will not work. So we have to work hard to control that. Next is phase control resolution. So that's what I was telling. Algorithm should be phase control resolution. So maybe it may vary in 0.1 degree, 0.1 degree, or 1 degree, 2 degree. So that's a kind of resolution we need to require. And second kind of resolution is that, so what sort of phase we are exciting into the element. So that also is there. Okay, what sort of phase we are exciting to the element. So whether you are exciting ideal phase, for example, if your design phase is 120 degree, it should be excited with the 120 degree phase shift. Otherwise, what happens is, so your beam will be beam direction may slightly changed. So that's why it is very important. Next comes, okay, once your design analyzed and your design is ready, next comes when you go for fabrication, you will face these many challenges. That is the opportunity for to explore. Okay, first one is that PCB substrate selection. That's just before I mentioned. So because substrate has substrate losses, thickness is involved, surface roughness, print antenna RF circuits. So which means what? So we are going to print antenna, RF circuits. So many components are going to be printed over the PCB, and also we are going for multi-layer also. So that is where then substrate selection will play a crucial role here. Next is PCB laminates and other RF components, availability in millimeter wave frequencies. So you can design any component you want, but it should be available in the market, right? So because you can come up with a fantastic design for different components with the some of their laminates. Okay, finally what happens is, when you go and explore in the market, it will not be available. So then your entire work is lost. So that's why please make sure that whatever components you use, so whether it is available in the market or not, that we need to ensure. Or else, so whatever design you are proposing, for example, some yellow components you may propose, but that should be feasible and best when compared to the one existing in the market. So that's also need to be ensured. Okay, so that's also a good opportunity, because for example, in millimeter wave frequency, getting in a component is very very difficult, because all are new it's a new band is open for 5G. So several components are being coming up. So best out of that component, so if you can come up with the best RF component design, for example phase shifters and several active components, so then it will be a very good contribution to the 5G industry. And fabrication tolerance such as track width, nowadays in India I can see that find one, I think in it's a very good lab, it may be less than that. Find one track width clearance is good. And via size, so because via size you cannot just drill 0.01 mm and all. Maybe it will be available in the very fine labs, but while analyzing your structures, we have to take care of this via size also, because you can come up with for example fantastic design like by drilling via, for example, 0.01 mm. In simulation you can do whatever you want, but that should be practically made feasible. That also involved. Next is cost. So that is where most of the industry is working in, because there are plenty of methods are already available. Okay, plenty of designs are available, plenty of things are available. But the one parameter where this all industries are competing is that cost. Okay, because I'm having very less cost effective solution, I'm having cost effective solution. So that is where it's with quality is important and also cost is important, because you can design propose a design with 5 crores, you can propose a design with 500 crores, you can propose a design with 5,000 crore also. So ultimately customer will choose 5 crore one only. But if you have a comparable quality with the one proposed with the 5,000 crore, if you have very good comparable quality, then obviously customer will choose 5 crore. Okay, so because cost also impact factor, important factor. Next is EMI issue in PCB stack up. Okay, EMI issue is a very serious issue, because hereafter signal integrity, power integrity problems are power integrity. So you can see that in several job portal, you can see that there are plenty requirements in signal integrity and power integrity jobs. Okay, plenty of requirements, signal integrity engineers for signal integrity engineers and power integrity engineers. Why? Because when you stack up multi-layer components and you are going to place several components together, so all will talk to each other. Okay, so intentionally or unintentionally. So those time, so EMI issue, electromagnetic interference and compatibility issue is very very serious issue, because you are going to have crores and crores of elements, components, tiny components in the one system. For example, node B. So in mobile, it maybe lakhs together components will be there in the tiny components. So if one does not work properly, for example, tiny component, for example, in terms of nanometer, so one does not work properly, then it will collapse, the surrounding also. So therefore, the EMI issue is there. So this is where you can see that there are plenty of requirements for EMI EMC engineers also, because EMI EMC was been there for several decades, but now it has become a serious issue, because we are dealing with the millimeter level, nanometer level, or even picometer level. Okay, so that point of time, so the EMI issue is the requirement is very crucial. Next is characterization. Okay, once you are done fabrication, everything is fine. Now how will you characterize? That also is a question mark. Like that is where several avenues for research and opportunities. Embedded and packaged array testing with the surrounding effects such as hands, cover, and etc. You have to test with all these scenarios. Otherwise, you have designed an antenna mobile, okay, which is working fine in the laboratory. When it is deployed in the market, that time they found that it's not working properly, because sometimes you are not getting signal properly and other things. Best example is that iPhone 3. I think they have designed an antenna in the surrounding, like for example, the rectangular box is there, right? So for example, is this so on the cover, then on the side walls, like 4 sides of the had an antenna. Okay, So when you hold your mobile and talk, at that time they were facing a lot of issues. I think that was published in several news also, I think. So what happens is, what was the problem? Then went on investigated that. Finally they found that, oh, this is the problem, because the antennas are on the side walls. So when the person hold the hand there, so obviously we are also made of dielectrics and water, and several contents are there. Dielectric will have finite conductivity. We also have a conductivity. So we may act as a ground. So we definitely affect the system, because we are also dielectric, right? Our dielectric also will interact with the antenna characteristics. Antenna characteristics will vary when you touch that one, because you are also dielectric. Then this effect will spoil the antenna's purpose. So then they gave free of cost, a special cover to overcome this issue. They gave free of cover for free cover for everyone. So that's where the testing is involved. Next is test environment. Okay, testing is okay, we can do this, but test environment. So creating test environment is another challenge, because you need to have a millimeter wave, you need to have absorbers ready, and how we are going to deploy, what sort of design for a scatter chamber they are going to use. So how best you can do for reflector design, feed horn design, and positioner resolution, and so how you are going to integrate with the several antennas, OTA measurement chamber you might have seen. So this proposing, analyzing this method is also a good opportunity for everyone. If you have very good understanding of how this setup works, and that also give you plenty of opportunities. Next is health issues. So need to be investigated before deployment, because I think several videos are coming up, like health issues are being coming up, like health issues are coming up, like several people are reporting that it's affecting birds and other things, but that need to be investigated before we deploy it, because once, if you want to launch the network, then we have to ensure these health issues are not there, because I think in Delhi, India, maybe in several parts of the world it was happened, especially in Delhi, they told that the pregnant ladies, a lot of abortion was happened because of high radiation. Okay, then they found and then fixed the issue, okay, after long travel. I think in several countries also reported, right, in US and other countries, several countries are reported this issue. Then there was a high, it was become a sensitive issue. Then government taken very serious actions. Many governments, like European commissions and US and Western countries, all Western countries, Southeast Asia, all they took this as a serious issue. Then they limited the then they proposed stringent conditions to radiate emissions control. They control the they want operator to be, they have imposed a lot of constraints to the operators to not to radiate beyond this limit. So that's where they propose the health issues can be controlled. Okay. Next is that general challenges. Next is general challenge. Okay, okay, we are done, and we are health issues, everything is characterization, everything is done. Next comes, okay, once you are done with all the testing, then next, when you are okay, you want to sell your product, then okay, then you cannot just once you are done with the test in your laboratory, you cannot just sell your product. Then you will have a compliance testing. So compliance testing means, so there are number of regulatory compliance. Okay, for India it is Telecommunication Standards Development Society, India. Okay, it's recently formed, for example, for India. Okay, department. So first time in the history that we are from Indian government in India has standards. They propose standards. I think FCC accepted that, and it will be a standard. I think large coverage and low power, some concept they propose, and the 3GPP everything is accepted. Then it will be a standard. So if you want to sell if your equipment you want to be sold in India, then it has to comply with that standard also. Okay, so that is where this regulatory compliance come into picture. This GBP is the general compliance, like minimum compliance that your equipment should have. I think this we have talked in several things in this about this in the previous presentations. You can refer those presentations on this. Next is emulation. So device testing, and I think this also we covered in the previous presentations. Device testing, RF protocol, RRF node, we also will have the similar kind of testing. Okay, so next is that simulation and testing. So I just want to cover one few things, like I have said, so integrated and design. So you cannot use one single software, you have to go for core simulation. Okay, for example, CST Simulation Studio, advanced design systems. So what happens is you design an antenna, you will import the S parameters of the antenna, then amplifier characterization, then this will go here, optimize, then these outputs will come into picture, integrated core simulation, then radiation characteristic evaluation, which means after designing antenna along with the after designing amplifier along with the antenna, there should be a change in the radiation characteristics. That also we need to evaluate. Finally, the diversity performance evaluation, polarization, the multiple things will happen. Okay, so this is how it will look like. For example, integrated design. You can see here that integrated design. You can see here that integrated design. You can see here that, so see, several components are there along with the amplifier, S parameter will be there, matching network, antenna port, MIMO, so transmitter chain, receiver chain, so all this coming up. Okay, and you can see here transmitter input matching network, output matching network, transmitter free amplifier, so how it will look like. Okay, and this I think we have talked in this previous presentation. So thank you. If you have any comments, please post here, and please, if you liked this video, please do subscribe my channel, and for the future videos I'm planning to, next time I'm going to make a presentation on polarization. I think one of the viewer asked about this, so that's why I'm preparing a material, and very soon I will post the polarization. Okay, thank you all for watching. Thank you. Bye bye.